Today I am going to design an inverter from schematic symbol to layout design. For this purpose, first we go to File, New Cell View. I'm just writing the cell name. First I will draw the schematic of the inverter. This is my device library. From here I am choosing the NMOS. Basically here I have 4 categories of device. I am choosing the normal threshold NMOS VTG. This is the length and width. I can change this if I wish. First I'm placing the NMOS here. Now I will place the PMOS. I'm pressing I for creating new instance. Here I am placing the PMOS. Now if I want to change this parameter, I will select the device, press Q, and I can change its length and width. Suppose I will choose 180 nanometer width for the PMOS. Now I am going to connect the nodes. For connecting the nodes, I am going to press Ctrl W. Only W. And I'm connecting the body of the NMOS should be connected to the ground and the body of the PMOS should be connected to the VDD. I'm connecting those. Now I want to include some voltage source. Voltage source is basically located in analog library. From here I am writing VDC for the voltage source. I'm placing it here. Now I'll connect it with wires. Now place a pulse voltage source. I'm writing V pulse and choosing this pulse voltage source here, placing it here. Now I have to include grounds. For this I am pressing I. Now I am typing ground. I have to place grounds here, here, and here. Now I'm going to connect these. Now I have to include a load. I am including a load capacitor cap. Here, connecting it with wire. Now I'm including ground for this load. I'll choose to place load this here. Now I will change the value of capacitance to a much smaller one. I am choosing 1 femtofarad as load. Okay. Now I am choosing this voltage, pressing Q and changing its supply voltage to 1 volt. Okay. Now I'm going to change the voltage level of this one. I'm choosing voltage 1 and 0. The period of the pulse, I'm choosing it to be 5 nanosecond. The rise time, fall times with the default values. I'm not giving any specific values. Sorry, I'm choosing the period to be 10 nanoseconds and the pulse width to be 5 nanoseconds. Okay, apply. Okay. I have completed drawing my schematic. Now I will just click this button, check and save. If there are any errors or warnings in the schematic, it will give me the errors. For example, if I delete this wire and do check and save, it's giving me warnings. So, and it's highlighting where from where the warning is coming. It will help me to find out any errors in the schematic. I'm connecting it again. Now check and save. Now I will do transient simulation for this inverter and find out that whether it's functionally working correctly or not. For this purpose I am launching ADEL here. From here, first I am going to include the model libraries for my devices. I am going to the directory where my model libraries are located. I am choosing all the models, apply. Okay. Now in the simulation setup analysis, I will do transient simulation now. So here tran, and the stop time I am choosing to be 60 nanosecond, accuracy moderate, apply. Okay. Now the outputs that I want to be plotted in the graph, for this I am going to outputs to be plotted, select on design. I want to plot this one and this one, input and output. Okay. Now I will just run the simulation, netlist and run. And this is my input and output characteristics. I would like to separate these two graphs so that it can be visualized more clearly. For this, I am just clicking this one, right click, move to new strip. It has moved to new strip. This is my input and this is my output. Okay, we can actually change this style width so that it can be visualized more clearly. Okay, now for example I want to calculate the delay time, rise time and fall time of this inverter. So I have to use the calculator. I can use the calculator tool of the Cadence. I'm going to tools, calculator. Now in the calculator window we will find a function panel. On the function panel, for example, if I want to calculate the rise time, I will go and find out the rise time here, and which signals rise time I want to calculate. I have to choose that. For this purpose, I am clicking this VT, and I want to calculate the rise time at the V out. So it will find out the node name of that portion. I will just cut and paste it in the signal. As I am calculating the rise time, the initial value will be set to 0 and final value to 1, from 10% to 90%. Now I click here apply. Okay, and I will click this green button here, and it will show me the rise time of the signal at different instances. For example, we can see from the graph the first rise time of the signal is calculated at here, this point, then at 10 nanosecond another rise time, then at 20 nanosecond another rise time. These are the rise times of the signals. Now if I want to calculate the fall time, then I'll again go to the calculator, and from here I will choose the fall time from function panel, special functions, fall time. Here I will again click on PT, choose this node, cut and paste in the signal. Now as I am calculating the fall time, the initial value will be 1 and the final value will be 0. Now I'm going to apply. This option will be multiple. We can choose it to be single one, as there are multiple rise time and fall time of the output signal. I'm going to choose multiple here. Now this will show me the fall time of the signals. You can see it from the graph. The signal first falls at 5 nanosecond, then at 15 nanosecond, then 25 nanoseconds, and goes on. Now if I want to calculate the delay of the signal, then I'm going to tools here. I will go to the function panel, special functions, and I will find out where is delay. This is the delay. The delay is between the input node and an output node. So first I'm going to choose the nodes. First I'll choose this node, the input node, and I'll just cut and paste it in the box of signal 1. Then I will choose the output node, and I will just cut and paste in the box of signal 2. My signal is from 0 volt to 1 volt, and their mid values are 0.5 for V in, 0.5 for both V2. And for example, I want to calculate the high to low propagation delay. For this reason, I am choosing, there is an extra F, I am deleting it. So I am going to calculate high to low propagation delay. For this reason, I am choosing rising for the input or signal 1 and falling for the signal 2, and it will calculate the delay for the third rising edge. You can choose any other 3, 4, 5. Actually in the graph you have a number of falling edges and rising edges. You can choose any one. Now apply here, and this is the delay. From the graph you can see at 25 nanoseconds, my input is rising and my output is falling. The time difference between the 50% of this input signal and 50% of this output signal is given as the high to low propagation delay. Now if I want to calculate low to high propagation delay, just change it to falling and change it to rising. Now if I apply and do it, and now at 20 nanoseconds, this one, my input signal is falling, output is rising, so it's giving me low to high propagation delay, this value. So in this way we can do transient analysis of the inverter and find out the different delays and rise time and fall times. Now we want to do this simulation of inverter. For this reason I'm going to close this windows and going to return to my schematic. Before going to my schematic, in the ADL window we can save our current states. It will save the simulation parameters and others, so that when I need to do the same simulation again, I can just load the state and simulate quickly. I'm going to save this state. I'm giving it a name. And saving. Okay, the simulation state has been saved. Okay, I'm just closing this. For DC simulation, I'm going to sweep the DC value of this input voltage. For the DC voltage, I'm giving a parameter name here, P in. Okay, now check and say launch ADL. Going to load this one that I have saved just right now. Okay, now I have declared some variables there. Copy from cell view this variable that I have just declared. I am just giving a random value that might be 1 volt within the range. Now I want to do the DC simulation. For this I'm going to choose analysis, choose DC, and for DC simulation I want to sweep the input voltage from 0 to 1. So I'm going to sweep variable from this design variable, typing the variable name in start stop. I going to sweep it from 0 to 1 volt. Apply. Okay, I don't want to do the transient simulation now. I'm removing the tick mark from here and I'm going to run the simulation. And this is my input versus output characteristics. We can just make the line thicker for easy visualization. I'm just making the lines thick. Okay. Now we can do also parametric sweep here. To do parametric sweep, I'm closing these windows, returning to the schematic. Nested parametric sweep, I am going to parameterize the width of the PMOS. I am placing a variable named WP here. The space, there should not be any space between WP nanometer. Okay. Now I am going to the ADEL. Now I am going to do nested simulation for this nested parametric simulation. So I am going here tools, parametric analysis. Now I will click add variable. Here I have to save this one first. And I can variables, copy from cell view, and I am giving any values here. Then I'll go to tools, parametric analysis, and here I'll see the variable list. I can choose the WP. I will sweep the width of the PMOS. For example, I want to sweep it from 180 to 400, and total steps I want, for example, 20. It will choose 20 values of width between 180 nanometer to 400 nanometer. Okay, now I'm going to press this green button to start simulating. The simulation is running. And it has plotted the 20 input versus output characteristics for different widths of the PMOS. We can zoom this graph and we can see here for different widths of PMOS, it's plotting the input versus output characteristics. In this way, you can do nested parametric simulation in Cadence. Thank you. In the next video, we'll show how to build the symbols from the schematics.